It's a technique, and you guys do pretty darn well with techniques. Our product rule, a chain rule, you guys are good at that. I kind of gave you some really tough examples to give you practice on how ugly these can be. The ones in the homework you'll find are a lot easier than the ones I am giving you here. But that said, it'll go fine. We'll practice and you'll practice and you'll have it pretty down cold by the end of the period. So here's the idea. The idea of the lesson is quotient rule for derivatives. When you take a derivative of a division result or a function that's a division problem. Now, you can do this by definition of the derivative, but it's kind of tedious and hairy. So let's do this a different way. You can actually figure out how to take the derivative of that on your own by using product and chain rule. All right? So that's what I want you to do on your own or with a Math Amigo. If you figure out how to take the derivative of h by using product and chain rules. Go. Notice, by the way, pause for a second. Notice I didn't say recall the quotient rule from your days in honors. I said develop the quotient rule now on the paper. Feel free to talk it over with your math buddies.
I mean, like I wouldn't
Feel free to dump the X, just use F's and G's. They are good Stanford. It gets a little wordy if you have the X's in here, so just call it FG. It'll be a little less ugly there. In our final form, we'll put the X's in. I know you know where it's supposed to end. Questions? Yes, you can. That is
Thank gosh.
Thank God.
Oh my God.
You will use the Lord's name.
I don't practically. Do you number one?
You never won.
I don't remember. Did you play Ed? Reminds me of it.
That's really good.
You just do it. Considering this on.
The chain. No, it's not a chain. Yeah, I didn't use it.
What do you do?
By using the product and the product.
You gotta use it. It's like a secret. You probably
Is it the
you I had a fun test right here.
By the way, that was on the board the whole time.
I know. My long lost.
Super duper. How do you go?
I don't feel like doing this today.
You know the color. You know the question. What question can you get there? Oh, it's close. It does not. It doesn't change one complete fraction. One complete fraction.
That's too much.
One big fraction. By product rule, what do I know that h prime is? First stays the same.
And you take the derivative of that.
Derivative of the second. Now that requires chain rule. Be careful. Okay, so when you take the derivative of g to the negative 1, what is it?
Negative g to the negative 2.
negative g to the negative 2, but then times the derivative of the inside, which is g prime. Chain rule. Plus, second stays the same, g to the negative 1 times the derivative of the first, which is f prime. Now that's a good start. That's the product rule. Now let's clean it up into one big fraction. Let's start by writing this as a fraction. How can that be written as a fraction? Negative fg prime over g squared. Beautiful. Plus f prime over g. Okay, that's fractions. That's nice. Now one complete fraction. Common denominator is g squared. The first term then is unchanged, negative fg prime. The second one we'd have to multiply by a g to get the common denominator, so we'd get f prime g. In the interest of making it something with a really cool mnemonic device, let's rewrite it as g f prime minus f g prime over g squared. That then is the quotient rule, to put in the box with arguments. If you had a quotient of a derivative of a quotient, like f over g, then it's g, sorry, I'm trying to use my mnemonic, g of x, f prime of x, minus, not plus, very common error, f of x, g prime of x, over g of x, that whole quantity squared, which is basically what we just developed. There's a really handy mnemonic. My goal, one of my objectives is that you will say this at least 10 times over the course of this period, so it gets in your brain. It goes a little something like this. Low, d high, minus high, d low. Now, Miss Kent says over low or something, which is wrong. Just kidding. I say it's over the square of what's below. Okay?
That's kind of confusing.
Yeah, but it rhymes well.
Low,
Low, d high, minus high, d low, over the square of what's below. Now, the most common error is people get the top mixed up. If you get the top mixed up and you say high d low minus low d high over the square of what's, it doesn't rhyme. Okay, so if you're saying it and it doesn't rhyme, then you did this part wrong. Let's try using it in action. Here we go. This is a quotient, I think you'll agree, so let's take the derivative. Low is x squared minus 1. It's the low function, no derivative. D high is the derivative of the higher function, that is the derivative of 3 to the x, which is 3 to the x. I said 3 to the x, I meant 3e to the x. Minus high, that is the upper function, no derivative. D low, what's the derivative of the low? 2x. Over the square of what's below, good algebra skills tell you, hey, I should put parentheses around that before I square it, so the whole thing is squared. That's the quotient rule. It's super duper easy. Now you try. Wrong one. Try the first and second ones on your own, and the implicit gets a little funky, so we'll probably do the implicit together. Okay, let's go check the first one. What's the d low, or low d high? What's the derivative of 2 minus x? one, yeah. Minus high, d low, derivative of sine is cosine. Did you get something like that for your first derivative? Check that. If you did, let me know. Otherwise, go on to the next one. These tend to get really wide. Okay, ready? Low is x to the 1/3, or you may leave it as cube root of x. That's fine. D high. Tell me, how do you take the derivative of 2 cosine of 2x? Okay, so negative 2 sine of 2x covers the derivative of the outside, but you have a function within a function, so you should pick up another 2 for the derivative of 2x. Did you get that chain rule piece? Minus high 2 cosine of 2x, and d low, you can leave ugly 1/3 x to the negative 2/3. And over the square of what's below, that's x to the 1/3 squared. X to the 2/3. All right, there we go. Moving on to the implicit. This is not too bad in first derivative, but in second derivative it gets pretty gross. I gotta tell you this. We'll just do first derivative today. Here's the idea. We're trying to find dy dx. So we're going to differentiate, but you can see we have a quotient now. So take the derivative of the first term with respect to x using the quotient. Low is y squared. D high, what's the derivative of x with respect to x? 1 minus high x. D low, what's the derivative of y squared with respect to x? 2y dy dx. You may, if you feel that this is getting bulky, you may use y prime notation. That's okay too. Over the square of what's below would become y to the 4th. Plus 2 minus, what's the derivative of y cubed with respect to x? 3y squared dy dx. All right. So that's the first obstacle, getting the derivative taken. There's some algebra that's a little tricky here too in solving for dy dx. What makes this gross is this dy dx is part of a big fraction. What can I do about that? You could, like, get a common denominator. Is that what you're saying? What?
Can't you just remove the other stuff from the side and the other side then multiply by...
The y to the 4th out? Oh, I didn't even think about that. Yeah, you could do that. Let me give you something else. If I have it'll be maybe one less step. If you have a fraction with a sum in the numerator, can I split it up into 2 separate fractions? You can. And so you could call this y squared over y to the 4th, and then 2xy over y to the 4th dy dx separately, plus 2 minus 3y squared dy dx. Then it's more like we've done before with a sum of many terms. So let's gather the dy dx's and do a little simple reducing if possible. This negative 2xy over y to the 4th. Reduce it a little, please. 2x over y cubed. That's that term. This guy over here, then, minus 3y squared, is also a dy dx term. So those will be on the left, dy dx factored out. Everything else gets moved to the right. So what's on the right side, please? Negative 2, and then a simplified form of y squared over y to the 4th. How about minus 1 over y squared? Cool? All right then, my final answer, not really cleaning it up, is negative 2 minus 1 over y squared over negative 2x over y cubed minus 3y.
So you're going to have the complex fractions.
It is. Any algebraic equivalent on the AP test is accepted. Okay? Which makes it hard for the graders because they have to do all the algebra to see if your answer coincides. Here we go then. Operating the technique, which I believe was supposed to say applying the technique.
Sure.
Here we go. One use of a derivative is critical number / extrema. Honors people, even you might have a little gotcha in here. This definitely got the BC students, so stick with me, please. There's something I want to talk about that tends to be a common mistake. So the critical numbers are the numbers in the domain where the derivative is 0 or does not exist, yeah? Anytime you find critical numbers, then you should start with the domain. The domain in this case is x what? Is not equal to 1/4 because that would cause a 0 in the denominator. All right. We got our domain. We'll make sure that I don't give a critical number that violates that. Now let's move on to the derivative. The derivative will employ a quotient rule. So do the derivative, and then we'll check each other in a second. So that's what my derivative looks like. See if you agree. In the previous problems, the question was find the derivative and stop. Now we have to go on, and so cleanup is going to be necessary. We're going to need to see when this is 0 or undefined, and I don't look at that and say, oh, there it is. I need to do more. So if I distribute, I get 16x minus 4, 16x squared, minus 4x, minus 8x squared, minus 4. Do you agree? Okay. I'm going to find where this is 0 or undefined in a minute, but I'm still not quite there. I have something like 8x squared minus 4x minus 4 over 4x minus 1, that quantity squared. All right. So where to from here? This would be undefined. Let's go with the two cases here. F prime is undefined if what happens? 4x minus 1 equals 0, which is x equals 1/4. Is that a critical number? It is not. That violates the domain, right? So that was a good candidate, but no, it's out. It's not in the domain. What about the derivative equal to 0? That would be where not the denominator equals 0, but the numerator equals 0. So let's focus on 8x squared minus 4x minus 4 equals 0. We could do quadratic formula, but is there an easier way? Take out a 4. I'm going to fight the temptation to divide it all the way over because I'm about to sign test and I want every factor there. I don't want anything changed. Does that factor? Somebody who's good at factoring, tell me, does it factor? Okay, how does it factor? 2x minus 1 and, oh, just a second. I agree with, let me get the signs. 2x and x and 1 and 1 because both are prime. What about the signs? Plus, minus, or minus, plus? Plus, minus to get negative 2x and a positive 1x. I agree with that. That then says x would, the f prime would be 0 at negative 1/2 and 1. Okay? Are those in the domain? Yes. So in terms of answering the first question, those are my critical numbers. Now the second part of this, if you remember way back when, was to first derivative test this for extrema. So if I write this, I like to have the first derivative all factored out if possible. I'm going to go back and write the derivative a little cleaner. There's the derivative. When you go to sign test, use all factors in the derivative. Here's what I mean. This is an issue on a test question for BC that they when I go to make my sign chart, I'm going to place three numbers. I'm going to use negative 1/2, 1/4. Did I get it right? Yeah. 1/4 and 1. Now the reason I'm putting 1/4 in there is, well, it's not even on the graph. It is an asymptote. It can cause the graph or the derivative to change signs here, depending on how the graph looks like. So if you don't keep it in your sign test, then you might be thinking a min when there's really a max, or vice versa. So always include every factor to the derivative, even if it's not a critical, because they are still places that the derivative can change signs. Here's the derivative. When I sign test the derivative at something negatively huge, ignore the 4, it's always positive. So at a negative big number, the signs would be negative, negative, positive, yielding a positive, implying F is increasing. Something just past negative 1/2. I could figure out a number, but gosh, that's some ugly numbers. Well, actually, it's pretty easy. 0 is a nice number in there. At 0, I have positive, negative, positive, and that's therefore negative, right? And so function's decreasing. After 1/4, it's not going to really change signs because that bottom denominator was squared, so it's still going to be positive, positive, negative, positive, so it's decreasing on the other side of that asymptote, and then something big, it's positives everywhere. So my conclusion then, F has a, what's going on in negative 1/2? Max or in? Hi.
Hi.
Max, thank you very much. F has a max at x equal negative 1/2. I don't know if I specified. I'm going to say where the x's are, the maxes are, not the F I use. Just give me the x. F has a max at x equal negative 1/2 because F prime changes from positive to negative. And F has a what about at 1? Actually, what about at 1/4? 1/4. Although it's included in the sign test, it does not count as a point, a relative extrema, because there's an asymptote there. So don't worry about extrema at 1/4. Just go to the 1 point. F has a max or min? A min at x equal 1 because F prime changes negative to positive. Okay. That's the application type. Let's go to numerically and graphically, and then we'll call it good. Say, then, you had a table of values for f and g at x equal 4, and you wanted the derivative. I would start with the general derivative. Don't worry about the table. First, tell me what the derivative is. Low, f prime, d high minus high, d low, over the square of what's below, g squared. Then say, hey, person reading this, I'm going to evaluate that at x equal 4. Then you can say, all right, this will equal, what's g of 4? 5. F prime at 4. Negative 3. F at 4. G prime at 4. Over g at 4 squared. 5 squared. So negative 15 minus plus 2 over 25 is Negative 13 times. You try the harder one on your own. Find h prime given that same table. This would be a commonly missed AP multiple choice. But not like this. Again, be careful of the chain rule there. Hi.
Hello.
Space. Oh, that is true. Would you, while you're doing this, check your work that you're not, remember, run on sentence of the general derivative into the specific, okay? You shouldn't have general, then go to numbers, unless you say, I'm going to evaluate this at 4 here. That's bad math to run the general and then start the specific and say they're equal. Okay, so after 4, let's see, does this clean up much? Did you get 29/12?
No.
Oh, okay, what did I do wrong?
I got 29/12.
Oh. You got what? Oh,
I got 17.
that's not going to be 29/12.
No, sir, that's not.
I don't think that's. So let's first of all check. No, that wouldn't be the issue. I'm not sure. Do you agree with f of x and the derivative of the top is this big crazy 1/2, 2x plus 1 to the negative 1/2, but then times the derivative of the inside 2x plus 1 gives you a 2 there, yeah? Minus high is the root, below is f prime over f squared. All right, substituting in then, I still have f at 4, maybe I put in the wrong, f at 4 is 2, 1/2, and if 4 goes in for x, then I get 9 to the negative 1/2, and the 2 is still there, minus f of the root at 4 is square root of 9, and f prime of x is negative 3, that's good, over 4, I think I'm good there. So did you get a 2/3 in the upper left product? Check your 3 components. Did you get 2/3 in the upper left product? Feels like you should, because 9 to the negative 1/2 is 1 over 3 times one of the 2's that remains. 2/3 sounds good. Do you have the signs right? Some people change that to plus. I don't know. Find your issue or let me know and I'll find it for you. Let's go graphically, shall we?
Yeah.
Say we throw a, I'm going to change that in a second, but I'll figure that out. Actually, let's say you try the example first, and then we'll try the harder one. See if you can do the harder one, but I need to make a small change to the harder one because it's undefined. So let's go with aha. Okay. G add 3. Is that a point or a slope? It's a point. What is G at 3? 3. F prime at 3. Is that a point or a slope? Slope. What is the slope of F at 3? Negative 1/3. Do you agree with the slope of F being negative 1/3? Okay. Minus F. What is F at 3, which is the point? 1. And what about G prime at 3? The slope of G at 3 is 1 over G at 3, which is 3 and squared. So negative 1 minus 1 over 9. Did you get negative 2/9? All right. Final challenge. Can you find that derivative, change x equals 0, which is undefined, to e minus 1? You'll see it works out for you. Change x equals 0 to e minus 1. Change the 0 to e minus 1. And that could be actually a little funky for the f value, but you'll work it out. Maybe I should change it to G. Maybe I should change it to D. Is it too late to change it a little bit more?
Yeah.
Okay, you'll be sorry. Go ahead. All right then. So be it. There's really only one ugly part to it.
No, Ellen.
All right. Do you have the derivative? Do you agree with my derivative? Natural log of x plus 1 times f prime minus f times 1 over x plus 1 over the square of the log statement. Yes?
Yeah.
All right. What about then at e minus 1? What is the natural log of e minus 1 plus 1? What is it? 1. That's log of E is just 1. F prime at E minus 1, which is about 1.7. That's the slope at 1.7, which is about, or is, negative 1/3, yes? Minus, here's the problem. F at 1.7. What is it? I don't either. That's what I wanted to change, but you wouldn't let me. So, although I could write the equation of F, put in E minus 1 and get a good answer, I do not want to take the time to do that. So instead, let's call it ballpark of about what?
3.5.
3/2. Okay, sounds good. I doubt it's that, but we'll go with it. All right, and what about 1 over x plus 1? 1 over e over natural log of e minus 1 plus 1, which is 1 squared, which is still 1. So, something like negative 1/3 minus 3 over 2e is your answer. And that's an estimate, so I should say that's an approximate, because the 3/2 was a ballpark. Okay, wasn't that good?
Yeah.
Questions on 40? 40?
Yeah.
Or did we get through all the questions and we just didn't want to turn it in because we're lazy weasels?
No, I think the first.
I might have had a question.
All right, 40 questions. Questions on 40. 45.
No, that's 41.
Oh, never mind.
Oh, okay. Okay, some of you have turned in fact, many of you turned in 40 already. Do I have anybody with 40 questions? Okay, on to 41. Then 25. Other questions on 41? One.
Oh, wait, no, it's
Not one. 20 what? 23.
Can you do 25 first?
Sure. You bet. Okay. 41, 25 is just sum of the first 200 positive integers. Really? This? You should know this.
Sorry.
Okay, do you know the famous story associated with this?
No, yeah, it was
Okay.
that smart tooth you found the trick.
Yeah, it is. Sorry. Indulge me. So this is an actual story. True that. About 300 years ago, there's this German classroom, 6-year-olds, okay? And the teacher didn't want to teach that day. He just wasn't feeling it. Go figure. So he says, all right, I'm going to put this problem on the board. It's actually 1 through 100. And he said, I want you guys to all figure this out and let me know when you're done. And so he figures that'll keep him busy for an hour. So he kicks his feet up on the desk to read the paper. But not maybe 20 seconds later, this kid comes up with this little slate, this little chalkboard, says, I'm done. And the guy said, just go do the problem, okay? I want to read my paper. He goes, no, I'm done. That's it. I'm good. 6-year-old. And it was exactly right. So, how did he add all those numbers in 20 seconds? Yeah. So, do you remember the trick?
1/2. Plus 1.
I went yes. Okay, so think rainbows, okay? Because that's what he thought. He said, oh, rainbows, 201. Oh, more rainbows, 201. Rainbows, 200. Look at that. They're all 201. And how many rainbows are there? There are 100 rainbows. And so, done. Okay?
That kid is smart.
Now yes, that kid was the greatest mathematician of all time, Gauss. Gauss. So this guy was so brilliant, he had a doctorate by the time he was your age. And by the time he was 25, he was so done with coming up with new theorems, he would just send them to other people and say, "Hey, take credit for that." Okay, there's tons of stuff that other people got credit for that he discovered because he just didn't care. He was amazing. All right,
I'm sort of busy that night, so why don't you just go?
you just go ahead and go present this paper to the Society of Mathematics. It's that idea. It's the rainbow kind of thing.
Oh, there's a replacement on 4.
Replacement on 4. And then 23 is first. Then I'll do 4. All right, 23. Is 23 still a question?
Not the opposite.
The opposite, like the negative?
No, like I spoke the numbers, and I went through a couple times and I didn't get it.
Oh, it's because they are idiots and they wrote their inequalities in the opposite fashion, greatest then least. So that's what. That's bad math on their part in my mind. I was always taught that's bad math. So, is that cleared up? Okay. 4. Question on 4 is the replacement. Just the answer is
Unless I get it wrong.
something like. Did I do this one? I can't remember if I did this one. Nope, didn't do it yet. All right, so here we go. Did you get? Probably need to go revisit this again. N of 1. What did you say for n of 1, which is 15? What does this imply?
Time equals 1 minute, there are 15 people in the room.
Yes, at time equal 1 minute. I like that you're using units. There are 15 people in the room. N is strictly about the number of people in the room, not about the rate of change. And time will be a rate of change. Let's start by taking the old derivative. Did you multiply it out, then take the derivative, or did you use the product rule to take the derivative? Product rule, beautiful. All right, first stays the same. Negative 1, derivative of the second, plus second stays the same. Derivative of the first. I get something like 16 minus 2t, which is not, I don't really care when that's 0 because they don't ask, but I do want to know what n prime at 1 is, which is 14. Now remember, sometimes it helps to write derivatives as Leibniz notation, dn dt, how n changes with time. Change in n, that's change in the number of people with changes in time. So interpret. At time equal 1 unit, minute. Number of people in the room is increasing. Interpret the sign is increasing at a rate of 14 people per minute.
That's sort of odd. Like, there's a lot of people walking in.
Are you kidding? We've seen you guys come in at the bell. There's at least 14 of you diving in at the bell. And that's in 3 seconds. All right.
Yeah, but we're desperate.
Hello, Natalie Gabbard. Please rise for the Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Okay. 40 is definitely due, but if you need till tomorrow at 41, I'll give you till tomorrow. The other class is a little more behind. If you're done with both, turn it in.